G'day everybody and welcome back to the channel. So I've had a bit of a think about this and I think I've got a good grasp on everything now. So here's what I'm proposing. I still want to play around with this a little bit more, but let's just go look at something on the computer first. Sorry. I forget to take the screen lock off sometimes. Let's just look at this first. Remember in another episode I was showing you guys someone else had pointed out using... I could never find the same comment about the sub rail on the negative rail, but I found this and it was talking about both the rails. And I thought, that's something we should try because, well, actually, in this situation, making the positive rail wouldn't help. Making it higher wouldn't help. But I was thinking if I do end up making a regulated negative rail, I might as well do the positive one as well, The other thing, I just had to laugh at this. You know how I was saying if I do end up using a Baker clamp diode, I'll definitely be adding resistance in series with it. Yeah, I found this. So I'm certainly not the only person that thinks like that. So I'd say I've got this down pat. I had a look at this too. Had a quick read over this. Look, this isn't going to help me so much, but it might help some of you guys if you want to understand what's actually going on here. So I'll just quickly go through the pages. I'll just move back so I can get it all on screen. Mate, that might not be big enough. Yeah, okay, I'll do it this way. So Baker clamp diodes. Tracking transistor. Now, this is where I had a bit of a laugh because, as we all know, doing this is going to cause the Miller effect, why can I not say this properly? The non-linear capacitive effect of the transistor will come into play the more resistance there is on its collector, turning it into a amplifier. You know what I'm trying to say. Anyway, and I need to talk about that too with this current source that I added. But anyway, we'll get there in a sec. And again, I got the right diodes. Thanks to people on forums and IvoLol for joining in the comments section. I'm certain that I have the right diodes. So thanks everyone. Anyway, back over here. So I just wanted to, like I said, this is literally got nothing to do with me. I'm literally closing that off screen now. Everything that's there I already knew. I already had the resistor idea. I just wanted to give you guys a look because I thought it does a really nice job of explaining what's actually going on. And I just thought it might be beneficial for some people. All right, so I've had to think about this. And I've done a little bit more reading too, how to look at other people's designs or their ideas that they propose to fix problems in their designs and even other people's designs. And I've noticed, I mean, in that example just there, where there was resistors to limit the current to the collector, there was 6.8 kilo ohm resistors going to the collector of the beta enhanced transistor. I think that is insane. The highest I was saying I'd seen and thought, like, to me 100 ohms is high. Someone said, yeah, going up to 1K is all right. Maybe. I saw 2K last night used, but 6.8 is insane. Here's the thing. Having this current source here, depending on how small the current is set, it's effectively like having a 6.8K resistor there anyway, so it's doing the same thing. So I don't like this idea, because whilst it really helps the VAS transistor not saturate, it turns this into an amplifier and its non-linear Cobb effects come into play. We don't want that. So what can I do to fix this? How can I still do what I'm trying to do? Well, I've done some more thinking. Now this is where I'm going to start doing a lot of experimenting. So first thing I'm thinking of doing is swapping some things around. What if I take this current source and turn it into a voltage source? Let's think about this for a minute. If you build a voltage regulator, on the output of that voltage regulator, if it's designed with headroom and good ripple rejection and filtering and all that, you've got really good rejection from the rail. So if I put a little VREG here where this resistor is, in the collector leg, it's off the rail. And then you guessed it, where the emitter resistor is, I'll just replace that with a current sink. So that's something I wanted to try. Then that just leaves the VAS transistor. Now, depending on whether I use the subrail or not, has a massive effect on the answers to this question, because, well, there's another two things going on here too. The subrail is helping me go down that extra 3.5 volts, and yeah, it helps to make this clip a little bit better. But how do I explain this? By having a subrail, it means it's a regulated rail, so it also provides, again, good rejection from power supply. What I'm getting at is, if I put a voltage source on this beta enhanced transistors collector and a current sink in its emitter leg, and this negative rail is still a subrail, that's fine. I'm not going to do anything here. But if this ends up not being a subrail, and I've got my voltage source there, current sink here, I'm going to want to replace this emitter resistor with another current sink or something. I don't know. I'm going to have to think about it, because I want it to have rejection from the rail. I'm thinking still the subrail is probably the best option here. It seems to help performance-wise too, and I'm trying to squeeze every little bit of performance out of this thing. So I think for the moment I'll leave the subrail hooked up, and I'll change this circuit so it's a voltage source. I've still got to work out how this is all going to work. You know, I've literally just come up with this idea, and I'm at the point now where I can't find any more research on this topic. Basically, what I have shown you guys I have found is literally everything I can find on the topic outside of other VAS designs. But in terms of improving this particular beta enhanced VAS layout with the current source at the top and nothing at the bottom, I can't find any more research on the topic. So from here on out, every idea you're going to see is purely my own idea, and we're literally just going to keep trying stuff. So it should be quite interesting. So without further ado, what I'm going to do, what I'm thinking is I'll still do essentially build a 3-terminal regulator job where the input will be the 0-volt rail, the output will be the emitter of this transistor, and the negative reference would be the negative rail. Yeah, I hope that makes sense. And then I can build a little voltage source, regulator, whatever you want to call it. I've got to put thought into this too. How do I want to do this? Because there's a million different ways of doing that. I mean, you could do it literally with transistors and resistors. You don't even need a reference. It depends on the accuracy, noise levels, a lot of things I've got to think about. The speed of regulation even. There's a lot of things to think about. So what I'm going to go off now and do is come up with a design for a voltage source to sit in between the 0-volt rail and the collector of this transistor. And then, well, I guess we'll test it quickly, make sure it still works. And then we'll put a current sink where this 470 ohm resistor is, and we'll see what that does. So this is going to be an interesting video. Alright, so I've been doing some thinking, and I'm thinking a 2N5551. But I'm also thinking about the topology of how I'm going to make the voltage source. Should I build a circuit to buffer, sort of like a buffer circuit that buffers the negative rail that's got regulation in it? When I say that, I mean a circuit that sits between the positive and negative rail and has like a push-pull output, and it's buffering the ground rail with some smoothing added to it, something like that. Or should I go for the 3-terminal approach that I was talking about, where I, input ground, output to the collector, and the 0-volt reference is the negative rail? Either way, whether I go single topology or dual buffer, whatever you want to call it, I'm going to use 2N5551s and 2N5401s. And here's why. They fit the criteria in terms of voltage, current, all that sort of stuff, power dissipation. But more importantly, excuse me, they are a low noise part. But even more importantly, the reason why I'm going for something like that instead of, say, a 2SC3200 or a KSA992 KSC1845 or a 2SC3206, the reason I'm going for that, see, these transistors, I've chosen them for low noise, high FT, low cob, very specific, a lot of parameters I've specifically chosen them for. Now, if it was a current source transistor like this, I chose the same transistor as that with just lower gain, because it sort of acts like part of the amplifier. It's the variable resistance at the collector where your signal's being modulated. So you don't want to use a crappy transistor there, right? When you're trying to create a voltage source, that's not a thing, if you get what I'm saying. So this is why I've chosen the transistor that I've chosen. So I just wanted to come on and just discuss that. I'm going to go mock up a circuit now, or maybe 2 circuits, and then we'll take a look at it. Alright, so this is kind of funny. I started building a capacitive multiplier. You can probably tell that's where I was going with this. And as I was inserting the capacitor, I started thinking about the logistics of this. The output impedance of this is still going to move around with current change. I don't think that's going to be a good idea, because it's going to be, again, similar to high value resistor, current source, blah, 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 you know what I mean? So now I'm thinking, okay, I have to go with some sort of a voltage regulator, right? So now I truly do I'm down to 2 choices. I've thought about everything, wrote everything out. do I create a sort of push-pull system that buffers the 0-volt rail? I guess buffering it's not going to really add rejection, but see, what I'm trying to grasp in my head is I'm trying to come up with a way of, can I buffer it in, oh yeah, that's the thing. I was thinking, yeah, buffer it in terms of DC, but clean it up in terms of AC, but it's still at what point? I mean, yeah, that's not going to work. And you run into all sorts of things like trying to work out time constants, and just becomes one trade-off for another to make things work. And yeah, so I'm really having a hard time coming up with what to do here. Yeah, don't know what to say. Gonna do some more thinking, but capacitive multiplier is not going to work here. I just want to point something else out before people start worrying. If you're thinking, holy crap, you're putting this much effort into the VAS stage, you know, adding riser boards, all this sort of thing, adding extra circuitry, how are you going to finish this amp? It's not all going to fit. The rest of this amp's finished. You know, I'm completely happy with the input stage I designed. I designed the output stage and driver stage and bias section years ago. I'm happy with that. Yeah, I've used better parts, refined values, all that sort of thing, refined the design, but I'm very happy with everything else. No, the only thing in this design that I'm actually not happy with is the VAS stage. And I'm happy with the topology because it, you know, the way it works really well in terms of reducing load off the input stage. You know, it's really good for low THD, but it does have its problems. You know, the sticky rail, saturating VAS transistor problem, and you know, it's heavily coupled to the rails. The collector of the beta enhanced transistor runs straight off the 0-volt rail. The emitter goes to a resistor to the negative rail, and the emitter of the VAS transistor goes to an even smaller value resistor that goes to the negative rail. So what I'm trying to do is keep that circuit exactly how it is and put stuff either side of it, around it. I don't, this is what I meant before when I said I don't want to, you know, add Baker clamp, add a tracking transistor, or add another stage or anything like that. I'm trying to keep stuff out of the signal path. So if I can, this is my whole goal with this circuit, is to try and do this without changing that, you know, audio in the base, out the emitter, in the base, out the collector. No other paths. Well, I mean, I guess the emitter resistor here, but you know what I'm saying. And here, but you know what I'm saying. Yeah, so that's what I'm trying to do, The other thing I wanted to point out is the next amplifier I'm going to be building, it's going to be basically, I'm really happy with this design, the way it's come out, everything except for the VAS. I'll be looking at building another design like this with a complementary VAS, but I haven't thought about the input stage yet. I'm not going to even start on thinking about that in this video, but I'm probably getting too far ahead of myself here. I haven't even finished this amp yet, but I just wanted to say that I really regret making this style of VAS but single-ended, because I think you guys probably remember I showed you some images with the anti-saturation diodes, Baker clamp diodes, whatever you want to think of them as. And that was this same setup, the beta enhanced VAS transistor setup, but it was a full complementary VAS. And I just got to say, that's the one thing that I wish I had have done with this when I started designing it, you know. But lesson learned. Anyway, I'm going to continue trying to work out what my best option is for doing this. All right. You're probably kind of confused looking at this, wondering why there's a Schottky diode and a normal diode and a transistor with a cap and a resistor that looks suspiciously like a capacitive multiplier that I just said I wasn't going to use. Oh, and furthermore, sorry, I've actually forgotten one component. My bad. So I have no idea if this is going to work the way I want it to work. The way I'm going to find that out is by testing. I'm not going to do it in the amplifier circuit. We're going to take this out of circuit. I'll explain in a second. Let me just get this second capacitor where I need it, which is on the output. All right, so let's go over what's going on here. Firstly, if we just, all this diode's doing is it's just making sure that the reverse voltage that goes from emitter to collector doesn't exceed the reverse emitter, base emitter, sorry, breakdown voltage, right? That's all that diode's there for. The resistor and this capacitor and the transistor are forming a capacitive multiplier. I had to think about it. The capacitive multiplier's resistance is going to go down as frequency goes up. And as I understand it, the most prominent spot for the variance of millicapacitance to have an effect would be higher up in frequency. I could be wrong there. Leave it in the comments if you know I'm wrong. I'm trying to get my head around this. But what I thought is, it's only for this one beta enhanced transistor, right? It's taking what, a milliamp 0.2, a milliamp 0.5. That's not much current. If I put a capacitor on the output of this as well, to stiffen up the output, this should cover me for my low frequency, and the rest of the circuit will cover me for my high frequency, giving me a solid output in terms of impedance and stability. I mean, from coming at the aspect of it's only going to have a milliamp and a bit drawn from it. I'm not saying it would be stable if you was trying to smack an amp on and off out of it or something like that, but for what it's powering, I think it's going to be rock solid like this. So the other thing this is where I want to experiment. So I'm going to have to take this out circuit. I think what I'll do, I'll set up a power rail and inject some ripple onto the rail, right? Remove this diode, and what we'll do is we'll just have a look at how much ripple comes out of here with and without the capacitor, obviously with this extra one removed for this test, so that will be out. Right, we'll have a look at how well it functions at removing ripple under, say, a 2 milliamp load with and without this capacitor, right? And if I'm happy with the performance of it, we'll stick this other capacitor in too, and just to have a look at how much more that improves it, right? And if I'm happy with that, we'll pull this back out, and this is where it gets interesting. I don't know how I'm going to explain how I've come up with this, but anyway. Baker clamp, and specifically a 5711 because it's got a higher forward voltage than, say, a BAT 42, 46, 48. Because I don't want the forward voltage to be too low, because I don't want to clamp the base entirely. But what I'm trying to do is I'm trying to stop the transistor from being able to turn on completely and go into saturation. Because in my eyes, every time it does that, it's just going to let full ripple and noise just pass through, or at least more of it. So what my thinking is I've actually had a lot of different ideas for this circuit. I've thought about putting a bit of a voltage drop in series with the resistance so the transistor can't be turned on all the way. And then I came up with this idea. So that's what I want to do now, is set up a power rail with some ripple on it and see how this performs at removing the ripple. And then, you know, I'll try a couple of different things like the Baker clamp so it can't turn on too hard. See if that affects the ripple rejection much or not. Maybe adding some voltage drop in here, like in the form of a diode or a Zener diode or an LED or something. Have, again, measure that. See if that affects the performance of it. There's a bit to go into here. So I'm quite interested to see the results. Yeah, so that's all I'm doing for tonight. I've spent like literally a couple of hours thinking about this. I know it probably seems pretty excessive for such a small thing, but I'm really trying to, like I said, preserve this circuit as it is and put stuff above and below it to make it behave better. And that has taken a bit of thought. Like I said, because everything's got its shortcoming. You know, you put a current source in the collector. Yeah, you can do that. It does work. It amplifies, blah, blah, blah. But it's going to cause a peak in the mid-band response. Probably do other things too. It's going to have varying millicapacitance effect on that transistor if I do that. You know, it's going to cause all sorts of problems. So, yeah. You know why I'm trying to do what I'm trying to do. So I'm going to go to sleep now because it's late as and I'm tired as, but come in the morning, hook this up to a power supply, either just a noisy power rail that I've just made out of something or one of my power supplies with some ripple injected onto it in the form of, you know, 50 hertz, 100 hertz, whatever. Because, you know, it's 100 hertz ripple that I'm primarily going to want to see the rejection on. But yeah, we'll have a play around with that and see what we get. I'm really curious to see how my ideas affect the circuit, you know, putting a Baker clamp on it so the transistor can't turn on too much. I'm really curious if that's actually going to, you know, we're going to have to look, obviously, low frequency content and high frequency content, because what I'm curious as to is, you know, like, can this diode stop the transistor turning on all the way, making it so that it still works as a capacitive multiplier, but at the same time, it doesn't do what capacitive multipliers do and let high frequency content pass through. So it's going to be an interesting experiment. It might yield no results, but all we can do is try. And if it doesn't, well, on to something else. Jeez, I'll tell you what, I didn't even get to the lab door to exit, and I realised, hold on a second, the 5711 is only a 15 milliamp device. I need something a little bit bigger than that. It's just a little bit too low. Alright, I've done a crap ton of work on this, as you can probably tell, and I just deleted all the footage because it was probably like an extra half an hour footage with me just swapping resistor values. I had the transistor hooked up back to front. Just a whole load of crap that you don't need to see. It's just going to waste time. I'm not going to deny I fucked it up. I had my emitter hooked up to my collector hooked up to my emitter. Yeah. But yeah, I didn't want to make you guys watch all that. I've also done a crap ton of research on this, where I was trying to work out the diode and I was thinking going for the higher forward voltage. That's probably not the best idea, because when you think about it, when there's those current pulses on the base, although I guess, yeah, I don't know, I'm going to have to experiment with that, because what I can't get my head around is the diode's forward voltage going to increase because it's going to have current on it, or is it not going to have current on it? I'm not too sure how that's going to work out in this circuit. Anyway, here's the good news. I ended up with a 47 mic These are low ESR 100 volt 47 mic caps, not knockoff ones, genuine ones. 33k load for 2 milliamps. I'm running this at 60 volts because I've decided to do it to simulate real world situations. Let's do an escape on so I can actually give you guys a look at how it's performing. And I'll just go grab a Schottky diode so I can jam one of those in there. I'll just grab a BAT 46. Turns out that also is probably a good starting ground. Going for a higher forward voltage, I'm worried if I get current on the diode and it goes higher, it might still allow the transistors to saturate, if you get what I'm thinking. Collector power's coming in, diode to collector. One moment. Alright, so the diode's in there now. Something's terribly loose, just give me a second. This was working perfectly. This is what happens with oxidation, guys. Overnight, I swear. You breadboard something and it's working rock solid steady, and you come back the next day and it's jumping all over the place. The wonders of oxidation. Alright. Now my waveform is stabilizing. Alright. I'll just get the tripod and I'll put you guys in the tripod. Alright, so that's about 3 point something millivolts, it's jumping everywhere. Just me talking is causing enough vibration. Yeah. Oh, God. Anyway, that's the output. I'm going to remove the Schottky diode. It's exactly the same. So, Schottky diode's not ruining... Oh, hold on a minute. 2.96, 3.1. Hold on, let me just put that diode back in. Oh no, yeah, it's exactly the same. Or is it a bit bigger? Oh, I think it's about the same. Hold on, I'm just going to take it out one more time. Yeah, no, it's the same. Oh, let me just look at the peak to peak. What are we at? 45, 39. 49, 37, 45, 39, 44. Yeah, it's about the same. So anyway, that's the output, and just for record, that's the input. Right, so there's what, 30 millivolts peak to peak, RMS, 400 millivolts peak to peak. So as you can see, this is doing an absolutely wonderful job. Don't forget, the circuit in question is probably going to have bugger all on the input and, you know, just a little milliamp load. Excuse the loose connections. Anyway, let's go back over to the desk. Something else I just want to point out quickly is that this circuit is doing better than what it looked like before on the scope. I had more wires attached to the breadboard going to my multimeter and that acting as an antenna, and that's what it really looks like. That spike you see is just a loose connection. But yeah, 40 millivolts peak to peak, 3 millivolts RMS. And if I move this over to the input, we're looking at 460 millivolts peak to peak and 29 millivolts RMS. So yeah, it's doing a darn good job. Alright, so I'm happy with the way this circuit's working, but you know how I've done a lot of playing around with the Baker clamp idea and all that, which as you can see is a different diode in there. I'm just recording this segment towards the end of the video to insert it earlier because I recorded some other footage of me playing around with this, and again, it was just too long and I was just wafting on, so I just deleted it. What I wanted to do was I wanted to show you guys some research that I discovered, because I've spent a couple of days looking on the internet about capacitive multipliers, and all I can find is capacitive multipliers that have a pass FET instead of a transistor, or a Darlington element instead of a transistor. I found ones that have got multiple R's and C's on the R and C network to the base to give more filtering. I found combinations of the two, and that's it. Apart from this one article, and I shit you not, this one article, I am the only other person I can find in the world that has even thought about trying to make this circuit better. I just think that's crazy. So without further ado, I'm going to show you this article because I think it's really cool. Like I said, I've been looking for 2 days, and all I've been able to find is how to give it more gain by using a better device, and how to filter more with more R's and C's. I've not seen anyone look into reverse conduction, reverse biasing, saturation, none of those points. I've not been able to find anything on that, and until I found this article, as far as I could work out, I was the only person that had even considered it. So I'm going to show you guys this article because it's pretty cool. Alright, so this is the article, or the post should I say. So KT88 says, intro. Since this post is quite long, I'd like to sum this up in a sentence. This post shows an issue with the operation of the well-known capacitance multiplier under appreciable load condition, with some background and simulation result as well as measured data. A solution to the problem is presented with some more simulation plus measurement data from comparison, as well as a rule of thumb for selecting the right parts for your needs. I want to share something I've noticed quite a long time ago, but up until now I was too lazy to sit down and write. Many power supply designs use the capacitance multiplier as a low-pass filter at the input to generate a clean DC supply for the error amplifier. The simple idea is to make a small capacitor act as a much larger capacitor by utilizing the fact that the BJT follower has an output impedance which is beta times lower than the impedance present at its base, with an additional RE, which is usually very small and can be neglected. However, there's one problem with this topology, which seems like many designs don't really take into account. Have a look at this simple circuit. So here we've got just a simple capacitive multiplier set up. Let me get something to point with. So here we've got the simple capacitive multiplier set up. We've got our R and our C on the base, and the output is just providing a clean DC for this error amplifier for this regulator circuit. For simplicity, the reference isn't shown. Anyway, it's a basic voltage regulator. I just explained all that. Anyway, however, once we start sourcing appreciable current at the output, the voltage across C1, the input capacitor, will fluctuate quite significantly. The exact value of the appreciable current will depend on the capacitance at the input of the regulator. the problem with this is that the assumptions under which the capacitance multiplier model was derived are no longer true. Even though the regulator itself still holds regulation as the voltage across C1 is higher than the Vout plus dropout voltage, this is no longer a circuit which can be approximated by a small signal model. If you look at the voltages at the terminals of transistor 1 under these conditions, it may saturate, and it may even work in reverse polarity. Here's the voltage collector emitter and collector current in milliamps of transistor 1 for this circuit with a 3300 microfarad C1 and a 1K plus 100 microfarad low pass filter on the base and a load of 1 amp. Excuse me. The results are from P-Spice with an error amp which is biased at 10 milliamps. As can be seen, the transistor conducts in both directions. I'll just make that larger so you guys can see that shot there. As can be seen, the transistor conducts in both directions, so the assumptions it acts as a simple capacitance multiplier doesn't hold. However, in some cases it can indeed be very profitable to use this circuit, and when it works as expected, it improves performance significantly. This issue is actually quite easy to fix with the addition of two parts. And here's what I was showing you guys. So it says the addition of D1 and C4 solves the problem. Under no load, it just adds an additional diode. Under no load, it just adds an additional diode drop to the dropout voltage of the regulator. So it would be best to use a low forward voltage diode like a Schottky diode to minimize this effect. However, under high load condition, where the voltage over C1 changes significantly, correct selection of C4 will prevent reverse polarity of the transistor and allow the capacitance multiplier to act as we assume it acts. The correct voltage value should be selected according to the line frequency and according to the current the error amplifier draws. The transistor can operate in the forward region with VCE above 0.2 volts, so we can allow around 0.5 volts of droop over C4. For instance, in this example with a 50 Hz input, 100 Hz after rectification, and a 10 milliamp in the error amp, you'll need math. Obviously using a higher value of capacitance won't hurt. But here's the simulation with these parts added, and as you can see now, the transistor is literally just doing its job and it's not conducting in the reverse direction. So my question is this: is this simulation lying, or does that really solve that problem that well? Anyway, let's continue. Just some more measurements. No load, with load, and then with the proposed modification, looks like it's doing a much better job. I mean, my circuit's already doing a good job. I just wanted to show you guys this because it's interesting. If you want to pause and have a read, I'll leave these last pages up for a few secs. I would like to point out another gain of using this circuit with the modification which might not be visible at first sight. Even though the dropout of the regulator is increased by another diode drop for DC input, this isn't the case in a real world situation. Since in practice the input voltage across C1 will drop significantly between charges from the rectifier, this circuit modification will actually allow the voltage across C1 to drop lower without affecting regulation. The reason for that is the following. The limiting factor for the dropout voltage in most designs is the path from the output to the filter cap C1 through the control node of the pass transistor base emitter drop of T2 in the schematics above. Through the error amp wait, what? I got lost there for a sec. Anyway, like I said, if you guys want to read it, you can read it. But okay, so the capacitor can drop. It can do a more better job without it being a problem for the transistor is basically what they're trying to say. What's this last page? Yeah, right. Yeah. So there you go. It says this trick can be used even without the capacitance multiplier. Just add D1 plus C4 and select the value of C4 according to the procedure in the first post. Oh yeah, right. So I guess they're talking about running the base straight from this node here. So it's just a voltage follower. Or, yeah, I don't know. But like I said, other than what I've sat here and tried to do on this breadboard with the capacitance multiplier, I've not seen anyone go further than, like I said, putting a Darling turner or a FET pass element in there, or adding more R's and C's on the base. This is the most I've ever seen anyone look into this, so I just thought I would just show that. Anyway, let's get back over to here now. I guess let's test it out in circuit. I guess there's no harm in trying it, but I just have a funny feeling that if I go and put a slower frequency square wave through the amp and it was loaded, that this circuit would not allow the collector to track, especially at lower frequencies, the rail voltage, and it might screw things up. So yeah, I'm going to have a little bit of a think about it. I might try it, I might not. Alright, bear with me here. I think I've actually cracked the secret to this. So, as I've shown, with the sub rail, it just cleans up a little bit of that bottom portion of the negative going clipping, right? And limiting the current to this transistor, which we can't do in the collector, but we can do in the emitter, either with a resistor or a current sink, really stops this from being able to saturate. So we know we've got two fixes. And then that leaves the fact that the collector goes straight to the AC ground and has all the noise coupled onto it. And I want to get a circuit in there to get rid of the noise. I think I worked it out. Because like I said, I've worked out how to make a capacitive multiplier that, how do I explain this? Has a stiff output, right? Which I think is going to benefit this quite a lot. I've worked out the Baker clamp. So I had it all wrong. I was thinking about this, and I was thinking about a transistor that's being used like open collector for its load. And yeah, you drain the current to the collector, but this transistor's being base emitter biased. So I took a Schottky and I pointed it from the base to the emitter. And as you can see, that drops way too low. Surprisingly, it's still filtering really good like that. I thought, well, I don't need it that low. And it still does its job, because when I wiggle the supply, remember this goes minus. Right? I've got my probes hooked up backwards. So when it's working, it's doing that, but it can never get too high towards saturation. And look, if I leave it like that and then go like that, it can get close to it. But with even just a 1N4148, watch this drop a little bit. Yeah? And then when I do that, it doesn't seem to want to go above that. So I think I've come up with a solution for a capacitive multiplier with a stiff output that can't saturate. And that's exactly what I want for this. The only thing I'm still trying to get my head around is, does this need like an accurate reference to the 0-volt rail, or does it just want a steady supply? I think I might be wrong with the fact that it needs to track the 0-volt rail. I'm going to go research that now, because that means everything with this. Because if it doesn't, and it just needs a rock steady DC supply derived from that point roughly, so it can swing either way, I don't see why this won't work. But if it needs a reference to the rail, then I can see this not working so well. So what I was thinking about doing now was just experimenting with just a couple of other diodes. I was going to go and see if I can find either some silicon diodes with a really low forward voltage drop that's lower than the 4148, or some Schottkys with a really high forward voltage drop. Just so that number, I'd be really happy if that was like 400. I'd be really comfortable with that. I feel that's like where I want. And you know what's funny? I wouldn't be surprised if a 1N5711 would do that. But because it's only a 15 milliamp part, okay, whilst the circuit's not doing anything now, I can put it in. But if I went and moved the rail around, I don't know. Actually, we could measure that. Oh, just a bit too low still. Okay. Just for shits and gigs, I'm just going to stick a 1N5819 in here. Yeah, I had a feeling that was a lot lower. Let me have a look through the diodes I've got and see if I can come up with a solution for this, because I'm darn close, I can tell you that. Alright, so I've just had a look, just a very quick look at some very basic surface mount parts that I've, not surface mount, through-hole parts that I've got. And interestingly enough, a UF4007, I looked at UF4004s, UF4002s, 1N407, 4007s, 4004s, 4002s, FR107s. I looked at a few different diodes, and surprisingly, the UF4007 at the 1 milliamp or whatever that source is, had a lower forward voltage drop by 1 or 200 millivolts compared to what the 4148 read. Obviously, it's a bigger diode too, so that's going to have something to do with it, because it's going to take more current to make forward voltage drop. But let's just see. Hey, that's beautiful. Not only it's a fast recovering diode, which is even better. You guys saw that. What did I say? I wanted 400. Get in there. I said I wanted 400. Come on, you really can't beat that. That is amazing. Hold on, let me just get this thing stable. Yep. Still working perfectly. If anything, it's working better than what it was. It's amazing. It's working really, really well. Probably because the transistor can, it's that just that little bit further away from the gate, the junction being all the way on, it's filtering more. This is working amazing. I'm glad I kept experimenting with my way, not what I just showed you guys before. And I'm not saying that that's not a good thing, but this only uses, oh well, I'm going to put the protection diode in there too for this circuit, I guess. So it's going to have 2 diodes, but still, I'm quite happy with this. You know, I mean, the protection diode just goes like that. What? Oh, I thought the diode made the voltage go up. I was like, what? The diode's leaky? So, that's it. I'm willing to put this in circuit now. Actually, there is one thing I still want to test. Let's look at the output of it, the voltage output in reference to ground. And I just want to twiddle my supply rail and put the analog meter on here and see how fast it responds, because I'm really curious about this. Yeah, really slow. I don't know if that's a good thing or a bad thing. Let's give it a try, hey? I'm happy with my circuit. So I'll stop the video now. Incidentally, I have finally found the article I was telling you guys about, talking about the negative subrail. Just the subrail and the negative. I found it. And I found a few other interesting things I wanted to show you relating to this design. So I'll take you back to the computer, show you that quickly, and then I'll turn all this off and start disconnecting all this and hook this circuit back up with these wires, and we'll power the amp up and see what we get. I've got to put all the subrail and everything back on, but that's all good. Sorry, I don't think I fully explained why I'm so confident now. So what I'm thinking is, if this works, this gives us our rejection on the collector of the beta enhanced transistor. The subrail solves all the noise getting into the emitters. Even what the 4 transistor current mirror, which does better than the 2 transistor current mirror for noise rejection, even what that can't reject, this negative subrail will really help with that. So the current sources have already got good rejection. And last but not least, I might add a current sink in the emitter of the beta enhanced transistor and see if that linearizes the clipping and fixes it up like it did putting it in the collector. I might also use the Baker clamp diode. It will definitely be the BAS21J, but with a lot of series resistance with it as well, so that, yeah, it's already 0.3 picofarads. It's going to have bug rule effect on it, but imagine with resistance in series with it, it's literally going to have no effect. So I think we've worked out all the shortcomings of this circuit and worked out fixes for it, and I don't think I'm going to be using the Baker clamp. From what we've seen, it looks like this is doable without it, so we'll see. But I do want to see perfect clipping, and I want to see it symmetrical and no little blip on the bottom half. If there is anything like that indicating that there's harmonics and distortion, then I will still, like I said, even if I've just got to add a little bit of a Baker clamp, like a highly resisted Baker clamp diode, like a lot of resistance in series with it, just because, say, the subrail, the cap multiplier, and the current sink don't bring it in perfect enough, and it still just needs that little bit more, then we can dial that in with the Baker clamp. And at least it's not just a direct diode across it. You know what I mean? So I'm really happy with what I've worked out here. No matter what, we've got an answer. So back to the computer now. All right, excuse me for holding the phone. I know you don't like it, it's shaky. I'm only going to be a sec. I just wanted to show this. Twisting the power wires that supply the rails and keeping them away from the ground is the best way of minimizing distortion from the supply rails, or probably the inductance of the wires and crosstalk and that sort of thing. I don't know why my computer won't let me load everything up. It's having like a glitch. This is the thing about the subrail. Okay, this is a way of doing it, and basically what's being pointed out here is the fact that this cap's here to filter the subrail, but this cap is attached to here instead of the ground point, so that it's oh, bloody hell. Let's just go back to the writing. It explains everything. The diode's there to stop C3 from being reverse biased. Anyway, and yeah, it's only halfway rectified. I probably do a more complicated, better job than that. But anyway, on to the reading. So I think this is the start. So yep, pause if you want to read that. Again, pause if you want to read that. Oops. Sorry if I've shown this in the wrong order or something, but I'm sure you guys that have paused and read it will be able to understand what's going on. But that's all I wanted to show you guys. Just what I dug up. Alright, back over here and set things up. Yeah, okay, I really didn't think that through. My apologies. I should have hit pause before trying to turn the phone around. Anyway, so basically what I'm going to do is our power source is going to be our 0 volt rail. Our output's going to be our collector. And our ground reference is going to be our negative rail. You know, I think what I'm going to do is I'm actually going to take that wire back to before the RC filtering on this negative rail. I'm going to have to put some thought into this too, because you see, what I'm doing here is I'm filtering noise and putting it right onto my negative rail. I'm sort of just, oh God. No wonder there's literally, from people on the internet, 3 solutions: tracking transistor, Baker clamp, and current limiting of different forms, resistors, current sources. And I think it was Texas Instruments added, like in the LM2907, an extra transistor with a current source. And not every single one of those solutions has got flaws in it. And I'm trying to come up with ways around this, but even my own solutions, I'm finding flaws. I see why this circuit, people love it because of the performance, but everyone's trying to work out how to solve these issues. It really is a tricky thing. I'm not going to deny it, but I'd love to be the man to solve this problem. So, obviously taking that and attaching it to the start of this resistor before the RC filtering for the rails, going to be some help, but maybe if I make the negative sub rail, I should take this back to like the start of it before it's filtering. I'm going to have to put some thought into that, but that's all right. Look, we don't need to worry about that right now to find out if the amp works. I mean, for now, I am going to take that off of that spot there and just solder it onto the end of this resistor, just for the sake of it. It could also cause some sort of instability or oscillation, injecting ripple and stuff there in between the input section and the VAS transistor's emitter. So I'll put that back at the start, but yeah, I will be investigating where to dump this noise at a later stage, because it's not going to get dumped just onto the negative rail like that. That's clearly not a good solution. I'm not saying all that noise is going to pass into the circuit, because, you know, like there's the RC filtering there and the rejection of the current mirror and that, but it's still going to get in, especially in the VAS emitters, and is still going to get into some point minus whatever rejection that current mirror has got into the input stage. So I will have to look into that. Something else that came to mind, you know how I was working out, by limiting the current to this transistor, the 3-volt sub-rail, it brought everything into linearity and made the clipping symmetrical and all that. The other thing we could look at, remember I was talking about adding R2, I've taken the load resistor out, but adding R2, a resistor essentially across this cap here. Well, if I did that, that would create some volt drop on that transistor, or some more volt drop, should I say. And I don't know, that might have some sort of an effect. Obviously, it's going to limit the swing, but I don't know what sort of an effect it's going to have on the circuit. It might bugger up offset. I really don't know. I haven't put that much thought into it, but I just wanted to point that out, that we potentially have another variable to play with. Like the 3-volt rail, sub-rails worked out, I know around 1.2, 1.5 milliamp current sink here should be about right for that transistor. Obviously, this is what I am looking at right now, but yeah, I wouldn't be surprised if that has an effect on it too. And so it's something to bear in mind. Have a look at this, guys. Back to the LM2907. The collector of the beta enhanced transistor is actually coming off of VCC, not ground. Now I'm going to have a look at the schematic for the inside of this op amp, because I don't even know if it's dual rail, like what the topology is. From what I'm seeing here, it's not set up like that, so that's probably why this is collecting from here, because everything's between ground and VCC. But I'll have a look at the rest of it, and if it's not that interests me, because I mean, you got your current regulator here, which is on the emitter, that's fine, but that goes straight to the voltage rail. There's no reason you couldn't put say a voltage regulator in here and get some rejection from the rail. And it's also not going to the AC 0-volt rail that all the noise is coupled to. So I just thought that was some food for thought too. Might look into this more for like my next amplifier design, not this one. I can tell you now, after discovering the shortcomings of this VAS, I've decided, like I said, the next amp will be a fully symmetrical VAS with said shortcomings addressed. Alright, I've got to go to bed. It is ridiculously late and I'm tired, but I'm too curious. So I've set this up. That's going to the start of that RC Networks resistor, collector, 0-volt rail, multimeter looking at the output to ground, scope looking at the output. I've disconnected the input. I've got the sub rail off, because the sub rail, and that article I read confirmed this. Well, I'd worked out myself anyway. The sub rail can't start up before the other rails. Otherwise, obviously it's going to make the negative side turn on for too long. So I turn my plus minus 60 on, and then I have the sub rail turned on at no voltage, just so that the pass element in the power supply is letting current flow, like 10 millivolts. And then I turn the other supplies on, and then I bring the sub rail up. But let me turn the supplies on, and let's see what we get with a capacitive multiplier in the mix, so to speak. Quite interested to know. Doing absolutely wonderful. That's great. Couldn't ask for more. However, on the output of my amplifier, I'm seeing a lot of noise that I did not see before. And it's 100 hertz. What do you call it? Yeah, what? Hold on, something's amiss here. Something's real miss here. I am not quite sure what's going on. But I have a ridiculous amount of noise. Ripple, sorry. Coming out the output of this amplifier. I'm just going to power this down. And I'm just going to effectively remove this from circuit. Power it back up. Oh, hold on, the same noise is on the screen with the amp turned off. Hold on, something's amiss here. What's going on? Something's amiss here because this did not happen the last time I looked at this. This is really strange. I don't know what is going on right now. My apologies. Let me just pause the video and try and work out what's going on here. Alright, well, it's not the amp, so I'm not worried about the amp, so I'll turn it back on. I just put my probe on ×10 and turn my scope up so I can't see it. It's just stuff leaking through from all these cables and supplies, obviously. I mean, the amp's not even on and it's still present. So anyway, back to what I was doing. Power this back up. Cool. Alright, I'm going to add the... Oh, whoops. I've got to put this back in circuit now. Alright. Powering up again. Alright. So that's up. I'm going to add the sub rail. Three volts. Alright. I'm going to... God, as soon as... just take you guys to the scope for a sec. Have a look at this. I'm just going to turn the sub rail off. Yeah. Talk about noisy. Definitely have to work on these supplies. Videos coming. Anyway, it's not the amp, so we don't need to worry. Let's put a signal through it. And let's see what we get. Jeez, the amount of noise. I don't know, something... I think something is up here because I don't remember having this level of noise before. I don't know what's going on. Oh, let me just check all my power cords. Alright, so what I'm finding now is that this thing's going into oscillation. I'll just take you to the scope. So as I turn this up, instead of it clipping like it was before, it gets to a point where it starts to do this, and I can hear the amp screaming, and you can see the ridiculous amount of current draw. Let's not do that for too long. And it's not until you saw that it stopped that it... No, it's still not right. What the hell? I'm just going to remove... You know, a lot of this could be due to the fact that I don't have the rest of the circuitry in here, especially the current source in the emitter path here, and the wrong value resistor in there. Maybe I should... Oh, well no, the current sink would replace the resistor. Maybe I should set up a current sink now. I think before I say that this is the problem, I've got a funny feeling that the problem's just that. Well, what I can do is I can turn this off. Yes. Turn that off. And I'll just bypass this cap multiplier one more time. And then I'll see if it still does the same thing without that in circuit. Alright. Turn the sub-rail on. Sub-rail's on. And let's go do the same thing again. Now, actually, no, I've already got a problem. I'm drawing a ridiculous amount of current for some reason. Let me just disconnect the input. You know what? There's some sort of instability here that wasn't here before. But at the same time, I am running the sub-rail without the current source that I had in the collector leg before, and that had cleaned things up. So maybe it's just that. No. Okay, so it's not the capacitive multiplier. That is wonderful news. Alright, well, that means I can put the capacitive multiplier back in circuit. That is not causing the problem. The problem is the lack of the current source. So I'm going to move this off to the side. And I'm going to build up a current sink to replace this resistor with. Like I said, I had a feeling this is going to be a 3-part solution. Part 1, sub-rail. Part 2, clean up the collector. Part 3, current sink here. Let's see if that current sink does what I think it's going to do. I'm going to go to bed now and do that in the morning, but at least I know where I'm up to. Alright, it's the next day, and I'm just about to set up this current sink, but what I wanted to look at first is I've just taken out the protection diode, and I've got my multimeter looking at the base to emitter junction. You know, with the positive lead on the base. It's an NPN transistor. So I'm going to turn the supplies off, and we're going to see what happens to the base emitter junction. Does it go negative? Does it stay positive? Oh, we definitely need that protection diode. Definitely. Alright, let's put this guy back in. Bit awkward. I'll get it. Whoops. I think I did something wrong there. No? What's it at 300? I swear this was at 400. What? I'm bloody confused. I swear I had this at 400 by selecting that diode. What on earth is going on? Hold on. Am I looking at something else? Just putting this extra bit of load on it. No, it drops lower with more load. Maybe it's because it's under more load. It's anything I can think of. Must be. Alright, I'm going to put this diode back in for protection. I'm going to turn the supplies off. And there you go. Now that is no longer an issue. I might even make that a Schottky diode. You're probably wondering why. Well, if there's current that flows in the reverse direction at any point in time, especially whilst the amplifier is doing its thing, amplifying, and that's a capacitive multiplier which is trying to switch the transistor against the phase of the ripple noise to cancel it out, having current flowing through the transistor in the opposite direction can't be too good for it. My thinking is if I use a diode that's got a lower voltage drop again than the transistor's junction, that most of the reverse current would pass through the diode, not the transistor, letting the transistor do its job more properly. I could be totally wrong there. It might not make any difference at all. You know what? I'm just going to go do some research quickly, see if I can work this out. I really hope I don't annoy people with how far I dive into things. But I mean, look, let me be honest with you, that's what this channel's about. It's about engineering, it's about trying to solve problems, especially things that have been problems. You know, if I can find 10 different forums that have got thousands of posts about something and there's still only 3 or 4 solutions, that to me is a big issue, this circuit. Anyway, I'm thinking about this because I reckon we should have a look at it. Yeah, putting the diode across the transistor stops, you know, current going through the transistor in reverse. Most of it's going to go through the diode, especially if it's a Schottky. But I'm just getting this article back up on my computer quickly, and I'll take a look at the page quickly, and I'll show you guys the bit I'm talking about. But I remember the guy saying something about having this diode and capacitor here to power this circuit. Let me remove my diode and correct it. Alright, and yes, I know that seems counterintuitive because you'd think that it would be passing noise out. I've measured it, it doesn't. Under load, under all different conditions, it works. And I think the reason why is because you already have your filtering here, so this is just passing a filtered node out. I don't think it, and the transistors, you know, got a lower resistance out swamping what that's. Anyway, that's not what we're worrying about. So what I'm thinking, the guy was saying that came up with this part of the circuit. He was saying something about it stops the transistor from reverse conducting and saturating, I think. So I'm going to go have a look at that article now, because if that's true, let's do that. Let's add these 2 components, remove that, and take a look again and see how it performs. Because I'll tell you now, if we can make the transistor not conduct that way instead of something else just conducting most of the current, that is obviously a lot better than just putting a diode over it. So I'm going to take a look at that now. Interesting looking capacitive multiplier, isn't it? You know what's funny? You could go on with this even more. I mean, you could put a FET here, you could put a Darlington transistor here, you could put, you know, like an R and a C here, and then another R, another C. You could really take this a lot further, but I find these components to be interesting because of the way they, you know, affect the performance of it in such a good way. All right, I'm just sorting out capacitor values, but I just wanted to talk about something quickly. At the moment, I'm using 100-volt caps. The transformers for the amplifier have arrived. I'll do a video on that, going over those in detail soon. So I'm going to have 54-volt rails in my amp after rectification. So I'll be using 63-volt caps, not 100-volt caps. So what I'm going to do quickly is I'm going to change these for 63-volt caps, still 47 micro, and I'm going to get a third 63-volt cap for this part here and work out the value of that. The 470 I've got, I think, might be a bit too big. I'll tell you what, for starters, what I'll do is I'll just take this diode out and I'll put just a 47, just the same as what we've got on the output, which I haven't drawn in there. All right, that's a little bit more technically correct now. So, oh, that's not a Schottky. Alright, I've just been comparing ESR between my low ESR and normal 47 like 100 volt caps. And there's a bit of difference there, but when I went and got the 63 volt ones, the ESR was like 1.3 ohms as opposed to 0.8 of an ohm. But I found these bigger 63 volt 47 mic caps, and these are coming in again around the 0.91 ohm. These 3 boxes went from 1 ohm to 0.8, if you're wondering. So these will do for the 47s. I've got that sorted out. I'm just going to go work out that first capacitor that will now power it off of this diode. Alright, I got this set back up. One of the wires was out before. I don't even think this was in circuit properly, but anyway, without the diode that I've used to clamp the base, under load it's actually 600 millivolts, and with the diode it's 468. So I might end up swapping that diode for something with a lower forward voltage drop again. But anyway, I'll look at that a bit later. For now, what I've done is I've added the diode and the extra capacitor. I guess the only real test I could do is take out the reverse diode, turn the power supply off, and see if this goes negative. Wow, it really does work. Wow, look at that, guys. You know something? The bloke that came up with that idea of adding that diode and capacitor is a bloody genius, as you can see. That is wonderful. It's on the edge of it. I'm going to make that capacitor 4 times bigger. I mean, yeah, it can go close to saturation still, but it's still quite a bit off. I don't know, maybe that diode is enough to stop it. But we certainly don't get any reverse voltage anymore with this diode and capacitor. So with my Baker clamp diode and that diode and capacitor added, like I showed you on that forum post, wow, I'm lost for words. The performance of this is just amazing. There's probably about a volt drop on it now. Dropout voltage, we can measure that. Yeah. So, you know, it's got about 1.2 volts drop on it. I'm going to try and lower the forward voltage drop on this diode that I'm using as a clamp for the base first, because under load that's a little bit higher. Like I said, I wanted that around 400 millivolts. It's now at 450, 480. I want to get that back down a bit lower. I'm going to do that, and then the other thing I'm going to do is increase the size of this capacitor just a little bit. Alright, I just did a little bit more playing around with this and just show you my findings. Just with the resistor without the diode and cap in there. With no load, so I disconnect. Okay, with the VAS connected to it, or beta enhanced transistor, when I turn it off, it actually doesn't go reverse. I mean, a little bit, but not, it doesn't skyrocket, right? If I take it out, I'll just power it up and power it off. Yeah. Straight into breakdown territory. let's run that experiment with the cap and diode with no load and see if it has an effect. And you know what? I'm going to go back to the 47 because I really want to know if this works, because a second ago I was going, wow, this works so amazing, but then I realized it was actually because it was loaded by my circuit. So let's see how it works. Oh, and I also have to hook the resistor up to this node here from the end of the diode to the base, so it now gets its power from there. Now we'll go back to the base, emitter junction. All right. Let's see. On, turned it off. Wow. So that dude is a genius. Not only it stops the transistor from conducting in the wrong direction, it does so much. You know, that with that diode there assisting, I think it's just really good. I wonder how it would work without the diode, because I mean, obviously the art of electronics is to try and get the best performance with minimal components and not waste stuff. Although I know the transistor can probably still saturate. I guess there's only one way to find that out. Yeah, I saw that shoot up towards 600 millivolts. Yeah, I'm pretty sure you guys saw that too. And that's with the diode in there. So let's just lift one end of the diode. What was that, 680? Yeah, that can saturate still, even with this circuit. I'll increase the value of this capacitor back to 100 and see if that helps. No. So it seems, this is interesting because it seems that the person who added this extra resistor and cap is a genius, and it seems I'm a genius. And when you put both of our works together with the already existing capacitive multiplier, you end up with a really good circuit. So kudos to him, kudos to me, and kudos to the original cap multiplier. We've all made it into something better. All right, I'm going to go find a diode with a slightly lower forward voltage drop. Like I said, I'm aiming for it under load to be around about 400 millivolt drop. So I'll be back in a moment, but I think that pretty much has me quite happy. I'm not even sure if I really need to bother sizing this any bigger or not, really. I mean, I'm not seeing any difference. I think because the load's so small, it's already got overkill capacitance, and plus the output's buffered by that cap. So I think 347s will be fine. I'm going to go and get a lower forward voltage diode, and I'm going to read over that article just one more time and see if I can make sense of the sizing of this capacitor. But I'm pretty sure it's just basically there so that, how do I explain this? It doesn't start to discharge before this one does, if that makes sense. I'll have to get my head around that. All right, I've fitted 100 mic cap there. I did end up putting the 100 in there, but I fitted a higher quality one, not the cheap one that I'd put there before. So two 47s, 47 on the output, 47 on the RC with a 470 ohm resistor, 100 on the input, all 63 volt caps. The diodes, I've left both UF 4007s, and the transistors are 2N5551. The reason I left that diode there was because I couldn't find anything other than Schottkys, which I think too low a forward voltage drop. And if I put like a smaller diode there, like a signal diode, like a 1N4148, hey, leave that, get out, get out. If I put like a 1N4148 there or something like that, because it's got such a small junction, it would saturate quicker than the transistor, and its forward voltage would go up, and it would allow the transistor to saturate too easy. So I think that's probably a good choice. It almost lets the transistor saturate, but just not completely. This circuit also helps it not do that, but it also stops it from reverse conducting. And that's really good because I don't have to have a diode pointing back at the collector from the emitter for protection, but the transistor can't reverse conduct, which stops current flowing back the other way. So I'm really happy with what I've got now. Really happy. I'm going to power it on one last time, and we'll take a look at the screen multimeter just to see what the what it looks like. Man, that looks like it almost saturated. What? I don't know, I'm not so happy about that. I'm going to take this diode out. I'm going to just let this drop all the way back down and see if, I saw that go up to 680 millivolts. With the diode out, let's see if it goes up to like 750, something like that. Maybe I will put a Schottky in here. We'll see. One moment, please. I'll tell you now, what I'm going to do is finish this, and I'll upload the video, and I'll just leave it in the title that it's basically a long video about capacitive multipliers, because I started making the video planning on doing work on the VAS stage, but I've put so much research and work into the capacitive multiplier. The video is basically just about capacitive multipliers, to be honest. So I'll do that. I'll upload it, and then I'll immediately add the current sync there and start working on the actual video about the VAS. Alright, that's dropped down to nothing. I did give it a helping hand, shorted out all the caps, but let's see what that peaks up to. I saw 675, and that's a digital meter. Obviously it's not going to show everything in a really small period of time. I'm going to go get a bat 46 again. I'll be back in a sec. Alright, the bat 46 is in there. I'm going to power on. Yeah, in my mind, that's a bit too low. Oh, I don't know what to say. Let me go grab something. I know this is sort of a little bit wasteful, but I've got some SS310 surface mount Schottkys. It's a 3 amp, 100 volt Schottky surface mount diode. And I'm thinking, because it's a bigger diode, 3 amp, it might have a higher forward voltage, and it might take some more current to get it to drop so low. I'm not too sure, but let's give it a shot. Alright, so after some fine tuning, I've made some interesting discoveries. Well, one more interesting discovery. So that's with the UF400A7 diode back going from base to emitter. And if I turn it on, it won't saturate. It'll go close towards saturation, but I mean, you saw that go up to 675, something like that. With this out, I did actually see it finally go up to 771. You guys saw that. But look at this. We can't use a Schottky either. And here's why. Because the Schottky's forward voltage drop is lower than the emitter to base junction, it discharges this capacitor through the diode into the load. I'll just show you what it does. So turn it on, looks all well and nice. Turn it off, Let's just wait a minute. All well and good, right? Let's continue waiting. Oh, something's happening. What's happening? Wait, what? Is it not doing it now? This is going to drive me absolutely crazy if the thing I want to show you doesn't work now. Have I set this up wrong? Something's amiss here. Hold on. Let me just power that up again. Something's not behaving the same way it did before. What? With the Schottky in here before, this was shooting up to like 1.2 volts. Minus. Reverse bias. Maybe I had to have the load removed to do that. Let's just try that with the load out for a second. This is a head scratcher. I swear to God, I just discovered something and now I can't get it to repeat itself. I might have to pause the video and test the components. I might have popped the transistor or something. Just make sure everything's making contact at all. Just try one more time. Ah, there you go. So you see what I'm saying. Maybe that's because something is not actually in. Let's give that a try, eh? Now I don't know what's going on. Do I have a loose connection now, or do I have a loose connection when it goes up to 1.2 volt? God. We will work it out. Okay, so you guys saw what happened. It was a loose connection. So this happened to me before, and it just happened to happen when I took this diode out and put the Schottky in, and the only thing I could think of was that the Schottky's draining the current off this cap quicker, and yeah, that doesn't fully make sense in my mind, but yeah, I guess it was just a loose connection, guys. Never mind. Alright, so I'm going to continue with what I was working on with here. So I ended up trying some different Schottky's, and yeah, I do have that 100 volt 3 amp Schottky. It probably would work. But I'm going to try one more thing that's probably a cheaper option. What if I add some resistance in series with that Schottky? I mean, I understand because it's a resistor on peak current, you know, voltage can form across that resistor and it can shoot up higher, but as long as, you know, it's a fairly small current load and the resistor value is kept fairly small, I think it's going to be alright. So I'll go grab, I don't know, I'll just go grab some random values. You know, I've got a 560 ohm resistor sitting right here. I'll put that in first. I reckon that's going to be a bit too high, but we will see. Oh, okay. I wasn't wrong. So maybe a 220. I'm going to go get a 220. All right, I've got a 220 in there. Oh, that still actually goes quite high. Maybe a Schottky diode is okay. I'll tell you what. I'll put 100 ohms in there. I kind of feel that going below that is just going to be basically the same as just having the Schottky in there on its own. So let's just see. Yeah, that can still basically saturate with the Schottky on its own. Yeah. Hold on a sec, my amp didn't start up. That's better. Stable. Alright, so I'm going to have to do some thinking about this. I'm surprised that the 100 ohms actually made that much of a difference. Let me go get some smaller value resistors. I've got a funny feeling that this is going to be doable, actually. Alright, I've gone down by an order of 10 again, so exactly 10 ohms. I'll turn it off. Turn it back on. Wow, even that still got up to 507 millivolts with a 10 ohm resistor. Let's just try that with the diode one more time. I'll just wait a little bit and then I'll turn it on so we can see how high it really goes. Alright, let's give this a look. I've just drained all the capacitors. Alright. Wow, that actually still went up to 412. I am pleasantly surprised. Let me just twiddle the rail for a sec. I'm really not seeing any change there. That's interesting. I am not quite sure why I'm not seeing any difference. Let me just take that diode out and do the same thing. No, so it's not the diode. Alright. I'm a little confused because why don't I see now, as this is doing its job, the base voltage modulate? Something's amiss here. Something just... God, how can this be so complicated? Such a simple circuit. Alright, let me do some more thinking. Alright, I've verified its operation. It is still working nicely as a capacitive multiplier. So I think, surprisingly, this is my final circuit. UF4007, 470 ohm resistor, 100 microcap, 247 microcaps, 2N5551, and a BAT 46. And I think I've finally made a circuit that can provide a really stable point to hang that transistor off with great noise rejection. Alright, I'm going to end this video here. I'm going to show you guys the updated schematic with I still left the two little legs for the protection diode that we don't have anymore in there. So that is my solution. This is the complete circuit, for those that are wondering. Now, this is only to supply max, a 2 milliamp load. Just bear that in mind. This is the circuit I've designed to supply a 2 milliamp load at about 60 volts. So if you want to steal those values, just bear that in mind. If you want the same results, it's going to have to be the same current area and voltage area. Otherwise, you're going to have to change values. Anyhow, that is that. Alright, I'm going to upload this video because, like I said, it ended up all just being on capacitive multipliers. So we'll get back to the VAS in the next video. Also, I wanted to say, if anyone is interested in this circuit, the modified version of the capacitive multiplier, not just the clamp diode, but this extra diode and capacitor, and you want to maybe see me do a video where I set this back up with that noisy supply rail and compare the performance of just a normal capacitive multiplier with the added, then against a normal capacitive multiplier with the added diode and capacitor, and also with the extra diode. Leave it in the comments. I'd be happy to do a video on that, investigating it, and we could play around with the input and the load and stuff like that and see how it performs, look at it on the scope, measure it in the time domain. If anyone's interested, just let me know and I'll do that. That being said, I'm going to conclude the video here. Thanks for watching, and I'll see you all soon.